Byron, welcome. Byron is the chief data scientist and co-founder at Tala, where he works to translate the latest advancements in machine learning and natural language processing to build AI-powered conversational agents. Byron also holds a PhD in cognitive and neural systems from Boston University. Welcome.
Hi. Thanks all for coming out to this session, the last one of the day. It's probably been a long day of a lot of exciting learning, so I'm glad to cap that off with you guys today. So tonight I'm going to talk about imitation learning, and specifically how it relates to reinforcement learning and this idea about for the real world. So I think the things I want you to take away from this talk, one is what reinforcement learning is, especially if you're not too familiar with it, what it needs to have to be successful, and sort of the challenges about making them practical. So how do we translate really exciting research that's going on in this area into something that we can use sort of in the real world? And by real world, I mean you're not Google. You don't have the resources of giant tech firms, or you don't have very particular kinds of problems. So how do you think about that? So again, just a little bit about me. We've already talked a bit about my background. I just want to highlight I'm on Twitter if you want to follow me there. I also post a lot of projects and things I work on in this space and others to GitHub. So these are some good resources if you're interested in kind of keeping up with stuff that I'm working on. But also, as you mentioned, my PhD is in cognitive neural systems. And one of the things I worked on there was about doing sort of taking models of the brain and how we think that we do things like locomotion and embodying them in robotic agents. And how do we train agents that way through sort of this self-supervised learning thing, which is similar to sort of this idea of reinforcement learning that I'm going to be talking about. And so that's kind of where my interest in this space really kind of took off. And then also combined with the fact that at Tala we work on sort of building a real product that we're trying to sell. And so pragmatism is really important when it comes to evaluating ML algorithms when we look at how to deploy them and how to consider them. Okay, so first let's just talk about reinforcement learning. It's really cool, right? Like there's all this cool stuff. We can play Atari games really well now. We can play Go better than anybody else in the world. We can do things where we can not only train agents to learn to walk, but we can actually get agents to learn to change their bodies to walk better. It's kind of a really cool trick there. This was a recent result that OpenAI trained 5 independent agents to work together to play the game Dota, which is a massively online combat game that you play against teams. And so this was even a more difficult challenge because it's a much more complicated environment and you had to have cooperation. And then finally, we see a lot of really great work coming out of Berkeley. Maybe some of you saw Peter Beal's talk earlier this morning. They do really fascinating stuff with reinforcement learning and robotics, and especially getting to do complicated tasks. So again, as a quick recap, we have machine learning. There's 3 kind of ways that we do learning. One is supervised, unsupervised, and reinforcement learning. And what is the point of these things? So we think of supervised learning as you're producing a prediction machine. I get an input, I tell you the output. Unsupervised methods are about association machines. We give a bunch of stuff, we want to learn how to combine things together. And then finally, in reinforcement learning, what we are ultimately trying to build is a decision machine, something that can take in an input and make a choice to do a task or to make an action. And this is important because unlike those other ones, reinforcement learning is an embodied learning because there is an agent. An agent exists in an environment. So there are some constraints here. And then the typical reinforcement learning process looks something like this. You repeat until you're bored. First, the agent observes the environment, which is what we refer to as the state. The agent decides what to do next, and this is referred to as an action. And then the agent receives some sort of feedback based on the action, which we then refer to as sort of the reward that the agent got. And so this can be sort of summarized in this figure right here. This is the basic reinforcement learning problem. Agent does an action in the environment, the state changes, maybe a reward is received. We repeat and we repeat and we repeat until we've learned or have accomplished the task that we've set out to learn. So the key question is, how do we figure out how to do that? So there's this idea of this decision policy. So in RL, we talk about the decision policy, which is what we use to decide what to actually do. And so this is really the core problem of agent-based learning. How do I figure out what to do given what I've observed and what I've done? And this is represented like this. We have some policy pi that is parameterized by some parameter set theta. takes in a state information of some representation of your state, and it produces some action. And so this is one way of representing this. Some people interpret it slightly differently in different contexts, but this is the basic idea. We want to find this policy pie that gives us the best outcome. And so how do we do that? How do we find good policies? And this is where the reward signal really comes into play. We need to understand what to do. And basically what RL says is we want to maximize this reward. That is the goal. Maximize this reward, or in some context, minimize a cost, which is sort of the negative of the reward. But that's the idea. We want to get the best possible outcome. And so we can represent it like this, that the optimal policy or optimal set of parameters, theta star, is the argmax over theta of the sum of all of our rewards over all time, given all states and actions. So how do we do this? So there's two big kind of ways to do this. One is to just learn reward maps. So we focus on the reward side of that optimization. We just compile a bunch of rewards. We do some things. We observe our rewards. We make a big table. If our table is too big, we approximate it with some function, like a neural network. And then we use that table to decide what to do. Based off what we've seen, we will make some choices, and we will sort of try to play that forward and think into the future, what should I do to maximize my reward? These are generally a collection of methods that are called value functions. The other way that's very popular is to actually just learn the policy parameters directly. And to do that, we actually just run a bunch of things. We take a random policy, we try stuff, we see the outcome, and then we collect that. And then we just use that information to sort of create a gradient over the outcome, and we update our weights accordingly. And these are sort of policy gradient-based methods. This doesn't care so much about needing to have a table of all possible rewards, just how did this particular outcome happen? Was it good? Awesome. OK, let's make that more likely to be good in the future and less bad in the future if we get a bad outcome. OK, so that's just really high level reinforcement learning problem and some basic ideas of how do we actually solve this. And so then I want to talk about, again, like we see reinforcement learning. It's in the news, depending on which news you follow. But really, like the DeepMind Open AlphaGo challenge was pretty big deal. And got a lot of attention. The Atari thing was also pretty big. And this OpenAI thing, I don't know how big it was broadly, but it was pretty significant for people who follow sort of these games. Because it was a major accomplishment to do the things that they did. So there's a lot of hype, there's a lot of excitement around reinforcement learning. And even you can look at places like DeepMind and OpenAI, and sort of the belief around RL is that it's going to lead us to artificial general intelligence, right? We need to have things that can make decisions in dynamic environments. And RL seems to be the best process we have to maybe get there. But reinforcement learning is actually growing. The interest in this continues to increase at a very heavy level. We can see that we're not even halfway through 2019, and we already see citations closing in on the number that we had last year. So this is a really big and hot topic, and people are doing a lot of work in all kinds of applications around reinforcement learning in the academic side. OK, so that's cool. But how do we apply this to real problems? Like, that's the point. Like, everyone's excited about reinforcement learning. We like this decision-making process. Lots of task-required decisions. But what we can do with this. So sometimes you'll see figures like this. So this was from a sort of a survey of deep reinforcement learning from last year. And they sort of picked all kinds of things that we could maybe apply reinforcement learning to. I mean, we have games, we have computers, finance, healthcare, education. Pick a vertical, and there's somebody who's like, oh yeah, we could use our reinforcement learning there. The problem with this is that sometimes it's just like, OK, if there's a consecutive decision problem, we can use reinforcement learning. And sometimes there's a lot of hype, there's a lot of excitement. I like to think of this as sort of saying, I have a transaction logging problem. We can use blockchain. It doesn't mean that blockchain is the wrong solution, but I think sometimes people get very overexcited about the potential of a technology without really thinking, is this the right solution? Can I get something else? And so we want to think about what's here. So what actually required by these methods? What made them successful? Because actually, most problems that you might encounter, and many of those problems that were listed on that previous slide, don't have the properties that these do. So one is simulation. You need to be able to simulate your environment. All of those cases, the environments were able to run in a simulated environment at high scale, because we need lots and lots of examples for reinforcement learning. If you start with an agent that knows nothing about the world, knows nothing about playing Atari, knows nothing about playing Go, and you want it to learn strategy, you need to have it lots and lots and lots of iterations to play. And this can run into the millions and billions of examples depending on the complexity of your task. So this is only achievable because we can simulate that problem. We can scale up. We have the ability to get and simulate this. And so it becomes more of a data engineering and a software challenge of how do I run more iterations? How do I run them faster? How do I collect more samples so then I can have more examples to then train on my learning algorithms? If your problem cannot be easily simulated, this becomes a challenge because that means you cannot collect the data potentially that you need to be able to train straight up reinforcement learning algorithms. And I just want to call this out. So again, the OpenAI 5 competition, or for the team that they created for the Dota challenge, they give some stats on their write-up of this. I want to call a few things. One, they collected 180 years of playtime in a day. And if you consider that there's 5 agents and each agent has to be its own sort of hero in this game, that's actually 900 years per day if you count each separately. That's a lot. And then each batch size. So each batch size of one training iteration, in this case, took over 1 million observations in one iteration. And they run about 60 of these per minute. So you're running about 60 million observations every minute. That's a lot of observations. So if your problem doesn't lend itself to this because you can't simulate it, you can't achieve this thing. Now, this is a very complex problem, and so they needed to be able to do this to solve this, but it's worth noting that this is what's necessary. Second is that it needs to be, often they're fully observable. So what this means is I have perfect information about the world that I'm in. So if I'm playing Go, for instance, I know exactly where every stone is on the board at all times, and I know whose turn it is. And so this means that the agent knows everything about the environment, about the state. But many real-world problems are only partially observable. So that means the real-world state is only given to us through some other means, like maybe I have an imperfect sensor, I can only capture some aspect of this state, and so I get some approximation, and I have to work from this sort of partial observability state. Another thing that's worth pointing out here is our algorithms, this is true for a lot of machine learning in practice, is that, how do you transfer this? If you do spend a lot of effort trying to train something up, and you finally get there, and you're like, excited, I got this. And then, again, we're in a real world setting, your boss comes in, or product team comes in and says, hey, the requirements changed, we need to adapt this feature, we need to add a new action to the state, or we've added a new capability. How do we do this? Can we just take what we did and add it on? Typically, the answer is no. We have to retrain from scratch. There's a lot of work coming up now about sort of meta-learning in R, where you sort of train agents to learn how to learn, for instance. And this is trying to get away from this problem, but it's still a very real problem. The other is, are the methods out there actually transferable to a variety of problems? So there's this real issue of reproducibility in reinforcement learning, especially deep RL, where it turns out that the same algorithm, the same code, run on the same task gives different results. And it turns out that it just has to do with the random seed initialization. So your starting conditions that you initialize has a big impact on how well your algorithm actually works on your task. Now, for a practical purpose, as long as I get a thing that works, I'm done, I'm happy, I don't care. And so maybe I just keep doing this until one gets out. But if I have to have a sense of, will I ever reach a good success rate? Or if I have to retrain because something changed, will I ever get back to where I was? Is uncertain. And so these are risks that we have to deal with. Okay, so again, we're back to how can we apply this, and it's worth noting that, again, these big successes are really games and robots. And that might have to do with the fact that they're flashy, they're exciting, they're very PR friendly. But that does seem to be mostly where we've seen the success, and it is because of what I just mentioned, that games can be simulated, they're adversarial, you can give all the information, it's very clear how to get rewards out of them, because the reward usually is either a score or some other thing that's well defined. And robotics, it's exciting because just building robots that can do things is a very difficult task, sort of in an arbitrary way like that. And so seeing these things on the robot side is really good. But for a lot of these other tasks, it's unclear exactly what, is there a big success in reinforcement learning yet? There's a lot of work trying to find them, but we haven't heard or seen anything on the level of game-playing robots. game playing and robots. With one exception, which I'd like to point out, which is around recommendation systems. So there's a thing called contextual bandits, which are kind of like reinforcement learning or RL light, which is, it's the same sort of RL situation. I have to make a choice, and I have to learn what choices to make. But I only have one state, and I get my reward immediately. I don't have some delayed action that I have to worry about. And so this is used a lot in things like recommending, say, for instance, what ad to show on a web page, if someone might click it. Or you could do it for song recommendations. So if I'd want to suggest what you should listen to next, I might use a contextual bandit to try to learn something about your preferences and then use that to sample from a range of suggestions without just sticking to like the one thing I know will always work. I want to be able to explore the possibilities without risking making too many mistakes. And so when we think about reinforcement learning and agent-based learning in general, it's worth thinking, what are we really trying to solve for here? Are we trying to get superhuman level performance on a task, or is human level performance good enough? What really is good enough for our task, and what's good enough in practice? So for instance, are we trying to beat the best player in the world at Go, or are we trying to figure out how to automatically track the action in a sporting event? Because in the first, obviously we have to be the best. We have to be superhuman. We have to be better than any other person in the world is. But in the other, it's just, we need to be good enough. We need to be as good as a competent person. So what does it mean to be human level performant? And again, is it the best? Is it we pick a thing? Again, is it in the case of AlphaGo, we beat the best player at Go in the world. In the case of the OpenAI, we're beating the top ranked teams in Dota. In the Atari example, we're beating Atari games better than any human could possibly beat them. That's one level, but then if we're trying to solve real problems, we don't necessarily need to be superhuman. We just need to be maybe as good as a human. We're trying to say, can I augment this function with an agent? And I don't need to be better than somebody. I just need to be able to do what they can do, but at a scale that they can't do it at. And this is a comment around people who claim like they've beaten superhuman performance on a variety of tasks, not just in in reinforcement learning, but machine learning in general, is that it's really important to ask which human are they comparing against. Sometimes it's just we farmed it out to Mechanical Turk. We asked a bunch of humans to solve some tasks, and we said that's the human level performance. But they might not be experts at that task, where the machine learning algorithms are trying to be the best they possibly can be. So it's mostly a comment that we need to be a little skeptical when we hear things about superhuman level performance. The other thing, and this is really important, and I talk about this as someone who has had to evaluate lots of different machine learning methods and what to apply in production. What is the cost of an error? And I think this is actually the fundamental question for deploying any sort of AI or any sort of machine learning, which is, what happens if you get it wrong? Because if we know something about machine learning algorithms, they're almost always going to fail at some point. We don't talk about things as always having like 100% accuracy. They usually have some trade-off. They have some F1 score, and we have to balance what their accuracy, their recall, their precision, against the benefits that we get. And so in the classification task, we often think about things like false positives versus false negatives. And in the RL case, in the agent-based learning case, we want to think about things like incorrect actions and how recoverable are we. So if I make a choice and that choice veers me off a cliff, that's pretty bad. If it drives me into a tree, that's pretty bad. If I make a choice panning a camera following a sports game and I get it off slightly, that's pretty recoverable. We're OK there. And so therefore, you can kind of balance, should I use an RL approach? Should I consider what I need to do to be safe? How do I balance what the cost of an action is? And can I recover from that action if I failed? Because again, in the RL case, we're doing iterative performance. And kind of related to this, there's a quote by Jan LeCun that was sort of repeated here by David Ha. If you use pure RL to train an agent to drive a car, it's going to have to crash into a tree 40,000 times before it figures out it's a bad idea. And this is the problem with pure RL. Again, you just say, here's an agent, here's a learning algorithm, go. And it can take a lot of effort, and you can make a lot of dumb mistakes. And so he goes on to say that one of the challenges here, and something that's very fundamental in sort of machine learning and sort of this AGI path in general, is how do we get agents, algorithms, to have a model of the world so that they can use that model of the world in an internal state representation so that they can actually play this through themselves. And so this second idea we can try really hard to figure out how to do this with agents. But the other thing we can do is we can use imitation learning. So imitation learning says, what if instead of having an agent just figure this all out on its own, what if we actually take a teacher? What if we take an actual expert and say, here's how you should do this. I'm going to show you how to do this. Learn from that. Learn from demonstration. In other words, why ignore a strong prior if it exists? If we already know how to do a task pretty well, and we can capture that task, why not start the agent off that way as opposed to starting it off from scratch? So imitation learning is this idea. It's essentially another type of agent-based learning. It's essentially supervised learning. So we've taken the agent-based learning problem and we've turned it into a supervised learning problem effectively. And we require sort of some expert demonstrations. So there's 3 broad types of this. Behavioral cloning, which is just, I've got a bunch of examples of someone taking in state information and making actions, and I just train it straight up on that. Direct policy learning, this interactive demonstration or sort of expert-based learning, where there's a teacher who can, or an expert who can give you feedback as you try things. And then this third idea called inverse reinforcement learning. And I'm not going to talk too much about this, only to say that inverse RL is actually a really fascinating topic of research, which is not so much about how do I find the optimal policy to maximize reward. It's what actually is a reward from a demonstration. So if I'm just given a video of someone doing a task, can I figure out what I'm actually supposed to be doing? What is the valuable thing? What is goal? Goal discovery is another really fascinating and hot topic right now in sort of agent-based learning. And so again, the idea is we infer the desired objective from the demonstration, not how to do it. And this is actually related to GANs in a similar way. So the generative adversarial networks, where a reward function is sort of the discriminator in our policy that we sample from is the generator, trying to sort of figure these interplays out. OK, so behavioral cloning. Behavioral cloning is very simple. Just do what I do. So this is, again, it's supervised learning. It's not expert systems from the 80s on agents, but it's supervised learning. We just say, OK, make an agent learn a supervised task. But this time, the difference is that our inputs are states, observations, and our outputs are actions, as opposed to, say, an input like an image and a label. And the key thing here is the expert who's creating these trajectories doesn't have to explain anything. We just have to collect the information. This was an input. This was the thing that happened. And we collect those pairs, and you train the model. So here's an example. We collected trajectories. So here's an example of sort of a game driving. This is Tuck's cart. So I'm driving a car around a track, and I want to teach an agent how to learn how to drive the car around the track. So first, I do this myself, or that player does this themselves in Cartridge because we feel we're pretty good at video games. We then break that up. So we slice it up by saying we've captured all of the video frames that we can see on the screen and the resulting steering actions that were taken. And then we learn them using some supervised learning method. Pick your favorite one. You could use SVMs. You could use deep neural networks. You could use decision trees. Whatever makes sense given the task you're trying to learn. This is behavioral cloning in a nutshell. This has a problem, though, because you can run into unseen states. You can have drift from the expert. So let's say I give you one trajectory of driving the track around, and the agent doesn't learn it exactly perfectly. It doesn't just copy and doesn't replay what I did. It tries to learn this model, and it will make some mistakes. And in the behavioral cloning state, example, it will get into a state that it has never seen before, and those results could be catastrophic. In this case, it could fall off the edge of the track. It could get stuck. It could just completely end up not functioning anymore in the desired goal. And so we need a way to sort of overcome this problem. So straight behavioral cloning may be OK if you have enough examples to start with. But if you don't, we need to solve that problem. And so, right. So we've got these trajectories. Oh, I'm going backwards. Sorry. Great. So behavioral cloning. So now how do we do a more efficient approach if we don't have enough? So there's this next idea I mentioned of sort of interactive experts, where we assume we have an oracle, which is either an actual expert, in this case maybe a human, or it could be just some optimal policy or some data that we've collected that is used as an example. And it's able to provide some sort of feedback based off of what the agent actually did. And one of the most common and popular methods for this is the DAGGER algorithm. So DAGGER is not one of the more egregious model name acronyms that I've seen. But basically, we just take this idea of data aggregation. So the key thing about DAGGER is very simple, and it's a very elegant idea, which is just, OK, collect some data, train your classifier, like in a behavioral cloning example, run the classifier against the task again, and then have an expert annotate those behaviors with the correct ones. Take those annotations, add them to your training set, and repeat. And you just keep doing this until you've achieved some level of accuracy or performance that you're happy with. And so the key here is, how do we create more trained data? And if you're familiar with something like semi-supervised or active learning, this is similar to active learning in a way for agent-based tasks, where I just keep asking for more and more examples if I run into a state I haven't seen before. And over time, the idea is that the number of states that we haven't seen will diminish and diminish and diminish, and you start asking more rare and more rare cases. And so again, really ask if uncertain. This is sort of this previous slide reduced to a pretty straightforward step, is you just do the task with the policy that you've trained. You ask an expert to correct the behavior that you did. And if there's anything new in that set, you include it into your new training set, and you go again. So you just keep going and going and going until you're satisfied. So when should I use this? Again, I mentioned this issue of cost. If we're talking about a real-world situation, you're not looking at a research project. You're not considering issues where this is sort of removed from the real world in sort of a pure simulation environment. If you're considering anything, and this is true for, again, I would argue, any ML project of any kind, you need to consider what is the cost of an error. And here I would say you want a low cost of error, because if there's a high cost of error, there's a lot that could go really wrong really fast with some of these agent-based systems. And then the state is easily observable. You want to know that you actually can see everything. So if your task has a lot of hidden parameters or latent variables or things like that drive it, you're going to have a much harder time using an agent-based learning system. And in particular, it may not be clear how to map that to the representations and the data you get from their trajectories. You want explainable actions, and by this I don't necessarily mean like the transparency and accountability stuff in ML. It's more like I need to understand that the action that the expert, the demonstrator, has taken is something that I can easily grok, or that I can easily capture and represent. So if it's something like steering, that's pretty straightforward. I have a controller, I push some buttons, or I turn a steering wheel. I have got a very small dimensional space of things I need to track, and they're all very clear. So that's good. If you're talking about trying to, say, track and get an agent to do, say, biomechanical mimicry or something, where I'm actually putting lots and lots of, like, say, tracking signals, like getting an agent to learn how to walk, then I have to sort of figure out, well, what am I tracking? How do I track them? How do I do that? I could take a video of an agent walking, but that's not a good representation of an expert. I could put motion tracking things on and try to do that, but that doesn't necessarily capture exactly what you need depending on your model. So again, you need to have actions that you're capturing in your trajectories that are easy or explainable or clear, so that when you do the training, you're not actually causing a lot of extra confusion. And then there's a reward signal. What are you trying to do? Sometimes a lot of work in agent-based systems is this idea of sort of reward hacking or reward shaping. If I define the task, I get to see what the reward is. If I don't get to define the task, I may not be able to define the reward, or I may not be able to get an easy reward signal. Something happened. Was it good? I don't know. How do I know? If I don't know if it was good or not, then I don't know that I can train on it. So if I have a lot of sort of ambivalent data, then that can be difficult, because then the agent won't really have a good idea of what's good and what's bad. So where can we use this? So an interesting task that I've been looking at a lot recently is around this idea of structured prediction, which is common in natural language processing tasks. So you can actually think of things like language modeling, like sequence tagging. So what is the part of speech of a tag? What is does a pronoun refer to? Things like that. You can do this as you can think of this as an RL problem, as an agent-based problem, where instead of I just have a sequence and I train maybe a sequence-to-sequence model in a more traditional supervised learning method, I can think about this as a agent-based system where at each time step, my agent has an action, and that's what is this tag? Is it a noun? Is it a verb? Is it an adjective? And then the state is the text that it has seen and the actions that it's put down in the past. And so you can sort of do this sequential step as an agent-based problem. And there's been a number of tasks that have looked at this in, again, like I said, sequence tagging, in named entity recognition, in co-reference resolution. And you can do this in language modeling as well. And so it's sort of it's a neat way of thinking about this. And so again, we can use imitation learning here because we have lots and lots and lots of trained examples of this. And we can take experts and say, OK, diagram this sentence for me, basically. And you're like, OK, well, you got it wrong. This is what you should have done. That goes back into the system. Other areas is continuous control. And in this case, I mentioned there's the pan and tilt at a sporting event. So if I have a camera whose job is to try to track the action in a game, if I have a human doing that, but I could have a robot do that. And so in this case, all I need is a camera that sort of says, OK, you need to be able to follow the action, or you need to be able to track where people are at any given time at some level, and then use that to inform what you're looking at. So here, I have potentially lots of data. I have lots of videos of actual demonstrations of what cameramen, the camera operators actually did. And so this way I can sort of say, well, OK, the action was going this way. What should I do? That they seem to follow something about this, and so I can track that. So we get lots of experiments. And this one, I actually like this idea a lot. This particular work was focused not only on how do we do this training, but also the fact that camera operation needs to be smooth. So we talk about an error in here. The error here is that I have a really jerky camera behavior. That's inconvenient and annoying for your viewers. It's not going to maybe cause serious problems, but it's going to annoy people, so we don't want that. And so here they actually said, well, OK, our behavioral cloning example mostly got us there, but it was really jerky. And so this work actually goes on to show how they can smooth this out to sort of filter these signals in a way to enable that more smooth motion. But what I like about this task in particular is this idea of thinking about imitation learning in a further sense. Like there's a hierarchical opportunity here. So like I could put lots of cameras around an event. They're all tracking maybe different things. And then, the idea of when you look at a live sporting event, you'll have the producer who's picking out which camera to focus on, which camera, which angle, which camera, which angle. That, too, is an imitation learning opportunity where you can have someone says, OK, I have my producer bot, my producer agent, whose job is to figure out which of my camera agents I should be paying attention to at any given time. And so you could have this hierarchical approach, which is kind of cool. And again, it can be entirely done through imitation learning because you have experts who are good at this, who can kind of show you, you can learn from. Where it would be potentially very difficult to do that if you're going straight from a pure RL approach. And then autonomous vehicles, and in fact, a lot of cases you can think that this is what people are doing. They're driving and logging lots and lots and lots of hours. They're collecting lots and lots and lots of data from actual, in some cases, experts who are driving the car. Tesla, for instance, is collecting data, right, on people who drive the vehicles. And so they can use that to say we have experts who are driving our vehicles, and that gives us more information in lots of scenarios, which we can use to improve the overall autonomy of the vehicle. And so again, here is the one that was done in simulation, but to show how we can make safe steering policies. And you can combine these, right? You don't have to have one or the other. So I can do imitation and reinforcement learning. So maybe what I do is I say I've got my imitation learning, I do my behavioral cloning as a way to bootstrap the process as a strong prior, but then I unleash my RL algorithm after that to say, OK, we've started here. Now go and see if you can, like, for instance, encounter some of the other rare cases that the expert didn't find, or maybe things that they weren't aware of. Likewise, if I know how to do a particular task, but I don't know how to do other things, I can combine them in such a way to take what I know, get the agent to learn that, and use more of the exploration-based methods where the agent does it itself in that context. And like I mentioned, there's these hierarchical approaches. So in this case, we use this work from last year sort of shows how we can use imitation learning and RL in a combined hierarchical sense. So in this case, we can say I can use imitation learning to learn sort of motor primitives would be an example, like basic movement motor primitives or basic actions in an environment. And then I can use RL to combine those, to try to chain them together in different ways. And so that's an option, or vice versa, that I can use imitation learning to try to do sort of more of the high level, OK, do this, this, and this, these sequence of steps, or the high level planning but RL maybe learns some of the more low-level aspects. Okay, so great. Why does this not work? What do we need to be careful of using this? Because otherwise, everyone would be using it, right? We wouldn't just hear about Go. We'd be hearing about all sorts of agent-based approaches. So there are some problems. So one, are the experts really optimal? It's entirely possible that the task we're trying to solve we're just not good at, or we don't actually have the best possible behavior. We don't cover the full space sufficiently enough. So what we're learning is not actually the best approach, and we might learn bad habits that could then hinder the agent's performance. The other issue here is, again, sort of the overfitting to the expert. So if the expert isn't really optimal, but we overfit to the expert using imitation learning, then we now have a problem. The other is scalability. Experts don't scale. If we talk about, you really want to do lots of training, I mean, it's one thing to say, okay, yeah, I'm going to have a person sit here and correct every label, but if I'm talking about driving around just even a driving and sort of continuous control task, and I need to say, oh yeah, you should have done this, not that. If I need to correct you, how do I do that? How do I say, oh, you should have really moved slightly to the left or slightly to the right when you didn't? That can be a difficult and expensive operation, especially with more complicated tasks. And then just how do we collect those trajectories? How do we get them so that we can even train? So, what is the representation of our state? What is the representation of the actions? I talked about that a little bit earlier. I could have non-Markovian behavior, which is to say that the expert is actually using information from the past that was unavailable to the agent, or is using some other outside information that is unavailable to the agent. So I might make a choice to do a thing, and then I might make a slightly different choice the same time next time, because I'm not going to pick the exact same choice. This can be difficult if that non-stationarity starts to confuse the agent. Likewise, I might use the world model that I have when I'm making choices about some task, which is not captured in the way you've represented your state. And so that can be difficult for the agent. So finally, things to consider. Again, low cost of error is really important, I think, if you're really seriously thinking about this. That your state space is sufficiently complex. So it's one thing, to be able to represent it, but you need to know that what you're doing needs an agent-based approach. You might be able to solve the problem as just a straight-up supervised learning problem with some heuristics or some other simpler tasks. So you want to have something where you're really, yeah, this is too difficult for me to solve with something simpler. The actions are consistent. Again, given a particular task or a particular state, I'm going to choose the same thing every time, given all the context available to me. Otherwise, the agent is going to have a difficulty deciding what's the correct path, and that you can actually collect this data. So this data is available to you, and it can be captured, and there's a way for you to think about this. So if the thing you're trying to process or the thing you're trying to evaluate is not easy to collect that data, it's going to be very hard to have RL or IL or any of these methods work. I did want to highlight again, Peter gave a talk this morning. He founded a company not so long ago now called Covariant AI. They are actually using imitation learning in practice in a robotics setting, which is really fascinating. So what they do is they want to train industrial robots by showing them how to do tasks. And the way they do this is they use virtual reality. So they have an expert who, in a VR environment, basically pretends to sort of be like a robot arm and does certain tasks, and then, say, moving blocks or manipulating things. And the idea is to use those expert demonstrations to help get agents, to help get these robotic agents to learn how to do these things. And so with that, I'd just like to close with a couple resources that are pretty helpful in this space. So one is last year ICML has a tutorial on imitation learning. This goes into a lot more technical detail about the various methods and the algorithms, and sort of highlights some different papers in this space. And again, challenges with these methods as well as sort of the benefits. And then Berkeley's DeepRL course, which is available online, also has a nice overview of sort of imitation learning and these tasks sort of early on in the course before they go on into a lot more about RL. And the last thing I'll mention about that is, again, if there's one thing I want you to take away is that imitation learning is not as exciting as RL in terms of like all the space of possibilities, because it does require humans, it does require a lot of training data, and that can be very expensive and hard to come by, whereas RL can just sort of, if I can simulate the world, I can just generate that forever. And so there's a lot of academic work on RL. There's some, but less on imitation learning, because it's, in some sense, not quite as interesting from a pure research problem, I would say. It's more of an applied problem, and that's the takeaway here, I think, is that imitation learning can be hacky to make it work. It can have issues, but from a, again, real-world setting of, I don't need the perfect option. I need a thing that works and that can be reliable. I think imitation learning is a much better place to start and to consider if you are considering doing some sort of agent-based approach to a task. And thank you. We have like about 5 or so minutes for questions. If you'd like to ask a question, please go up to one of the mic stands.
Hey there, really interesting stuff. Can you, and I'm really most interested in this, the combinations of the IR and ML, or RL and IL techniques. So can you talk a little bit about maybe some examples you've seen that really work there, starting with IL and then going to RL? So you talked about using experts like to be the feedback loop. Are you using like a reward function to be the feedback loop in kind of a second state? And if you have examples there, I'd love to hear more about that. Yeah,
so the question is, are there, have I seen examples of where there's this combined usage and sort of how do people do this? So the answer is, in some sense, that I've only seen a few, honestly, and like this one that I highlighted previously was probably the main one that, actually, I'll just leave it this. Where people have used it is in this, the hierarchical sense, especially, where I essentially want to train an agent. In this case, they played Montezuma's Revenge, which is an Atari game that was notoriously difficult. Uber, AI Labs actually came up with an RL solution to that game finally late last year. But for a long time, it was a very hard problem to solve because the rewards were very, very sparse. Like you could just flail around, you could do hundreds of millions of simulations, but you would never actually get any real reward because it's such a kind of confusing exploration style game. And so in that case, they showed that you could use imitation learning because you could say, okay, I know what you should do. I'm going to tell you what to do, but I'm going to let you explore at the same time. We can do this in a hierarchical fashion. And they were actually able to show that, at least at that time, that was a pretty impressive result to essentially combine the exploration features that you want, because you don't necessarily know the best way to do the full task, but you do know that the pieces, you can give guidance to say, well, there's objectives that you need to solve, and I can help you in that sense.